So have a look at page 15. This one talks about path difference. The arrangement that is used to demonstrate interference with waves on the surface of the water is shown in figure 7.1. Two dippers D1, D2 are connected to motor and a DC power supply. Initially, only D1 vibrates on the water surface to produce water waves. The variation with distance x from D1 of the displacement y of the water at one instant of time is shown. Okay, so what they're basically telling here is that this is actually a ripple tank experiment. You have two dippers, dipper 1, dipper 2. They are connected to a vibrating bar. The vibrating bar itself is connected to a power supply. It is actually this little thing here that you see inside your notes, page 6. All right. So what they're basically telling you here is that they only let vibrate dipper D1 vibrate first, and then after that they plot the variation of the displacement of water with distance. Okay, so what they say here is that when your dipper vibrates, it will generate water waves. They're plotting the displacement of the water waves with distance. And this is what you see. So they want you to determine, in your case, the amplitude of the wave, the wavelength of the wave. This one should be quite straightforward. This one won't take you a long time to see. They want the amplitude of the wave. Amplitude, you know, is this one. This one is going to be 2 divided by 5 is 0.4. This one will be 3.2. So amplitude is 3.2 millimeter. Okay. Next one, the one wavelength of the wave. This is one complete waveform. That will mean that this one is your wavelength, which is at 20 millimeter. So wavelength is 20 millimeter. Okay. Right, so this one is okay. The next one is talking about something else, all right, more appropriate to your current level. Okay, now they tell you the two dippers D1 and D2 are now made to vibrate, and the waves produced by the waves are produced by both dippers on the water surface. All right, both dippers are vibrating. Waves are now produced by both dippers on the water surface. State and explain whether these waves are stationary or progressive. Okay, this one I can just tell you that they are progressive. Wait on November 15 P22. The waves are progressive. All right. The reason is because the wave fronts move outwards from the dippers. All right. If you remember that little video that I mentioned to you guys before, let me just show it to you guys just to refresh your memory. This one is progressive wave. Okay. So one of the things that was mentioned to you is that progressive waves have wave profile that moves from one point to another point. You could imagine that this one is your wave profile. Okay, this one is your wave profile. This wave profile over time will move. It could be that this one is at t equals to 0. At t equals to 1, it could be over here already. At t equals to 2, it could be over here instead. Okay. So with each second that passes, that same wave profile will move from one end to another end. You can see it doing something like this now. Okay. So of interest here is that you see the wave crest is actually also moving. At the moment your wave profile is moving, your wave crest is also moving. So let me just freeze it at the appropriate time. You notice that this one here is your wave crest. Okay. Notice that this same wave crest, as the wave profile move, the crest is also moving along with it. All right, the crest is moving along. So over here in the question, they ask you to state and explain whether the waves are stationary or progressive. You should just say it's progressive because the wave fronts are moving outwards from the dipper. All right. The other video I need to show you is the interference pattern formed by ripple tank. Wait, now let me open up that little part. Okay, ripple tank. You should be able to see this. Okay, so this is the interference pattern formed by your ripple tank. Okay, so that time I specifically mentioned to you that these regions here is where you have constructive, and then these calm regions here is where you have your destructive. Okay, so if you look at the calm regions itself, your wavefront is this one. Okay, this is your wavefront, which is actually your crest. Okay. Notice that if I replay the video, that crest, that wavefront or wave crest is actually moving from one end to another end. So yeah, this is progressive wave. Okay, right. So let me just go back to that little example. Okay, so yes, the waves are progressive because the waves are wave fronts or wave crests are moving outwards from the dipper. Okay, stationary wave, that one will be under next week's lesson. All right, you don't need to bother so much about what is stationary waves first. That one is under next week's lesson. But you learn progressive wave. From that definition alone, you can do this. Progressive because the waves fronts are moving. Okay. Now, explain why D1 and D2 would be connected to the same motor. Why are they connected to the same vibrating bar? Why are they then connected to the same motor? So one of the things that was mentioned to you, it is so that coherent waves are produced. Or you could also say that to produce waves with constant phase difference. So one of the reasons why you want coherent waves, as I mentioned last time, is so that you have a steady interference pattern. That one I explained to you under page 3. No, was it 3 or 4? Sorry, I explained it under page 5 of your notes. Coherence is meant to ensure that your interference pattern is steady, meaning to say your constructive and destructive regions don't simply change location with time. It is fixed. All right. Okay, so that coherent waves are produced in your case here. All right. Okay, now then look at part C. This one is talking about path difference already. 2 points A and B on figure 7.1 are at distances D1 and D2 as shown in figure 7.3. Okay. State and explain the variation with time of the displacement of the water on the surface of point A and on the surface of point B. Okay. So right now, what they say is that you have 2 points to consider. Point A, point B. All right. They want you to identify what is the nature of the oscillation at these 2 points. Okay. So they made these little lines here connecting the points with the dippers. Notice that D1 will travel this line to A. D2 will travel this line to that same point. There's actually a path difference here in terms of the distance that they travel. So this one will determine whether you're going to get constructive or destructive here. You could also say the same thing for the second point, point B. You again have path difference. Wait, let me just see what line can I use. For point B, D1 will travel this much. D2 will travel this much. Okay, so again, there is a path difference in the distance that they travel. This is again your path difference. Okay. They again will determine whether this is constructive or destructive. Okay, so they've already given you the distances over here. D1A, D2A, D1B, D2B. So they want you to then determine what is the variation with time of the displacement of the water wave at those specific points. So here, the easy thing to do is to find the path difference and express it in terms of fractions of lambda. So what you do is you first say this. Path difference D2A minus D1A, it will be 7 minus 5 equals to 2 centimeter. Now you want to express it in terms of fractions of lambda. So you already found out the lambda actually in the previous page. It is 20 millimeter or 2 centimeter. Okay. So here I actually change it to millimeter now. 20 millimeter divided by 20 millimeter gives me fraction of a wavelength. I'm actually getting just wavelength itself. So here I would say that constructive interference occurs. The water oscillates with an amplitude of 2 times 3.2, 6.4 ampere, 6.4 millimeter. Okay, wait, let me just write something for you guys. Constructive interference, I mentioned to you path difference must be 0, lambda, 2 lambda, 3 lambda, dot is n lambda. Destructive interference is where path difference is lambda over 2, 3 lambda over 2, 5 lambda over 2, dot. In other words, it's going to be this one. Okay, it's always 0.5 lambda. Okay, equals to n plus half lambda. Okay, so because you see that the path difference here is lambda, therefore it's constructive. No? You can actually write this in between the statement. Constructive interference occurs, therefore the water oscillates with amplitude of 2 times 3.2 equals to 6.4 millimeter. Why is it 2 times? You see at point A, wave from D1 will be like this. It will be having an amplitude of 3.2 millimeter. I know D1 will arrive at point A first. D2 will arrive much later than D1, but it will arrive one wavelength later. So say this one is D1. Wave from D2 will arrive one wavelength later. Okay, one wavelength later, it will arrive like this. It also has an amplitude of 3.2. Okay. So what you do know is that the waves meet constructively when your path difference is lambda. So it will give you a new resultant wave like this. So according to principle of superposition, your resultant displacement is the sum of displacement of the individual waves. So this one is 2 times 3.2, giving you 6.4. Okay. So this one is wave D2. All right. So that's why it's double the amplitude, 6.4 millimeter. Okay, so if that one is okay, then you move on to part B. Part B is something similar also. You find out the path difference, okay? Just find out the path difference where you say something similar like this. You see that path difference is the difference in the distance traveled by the two by the waves from the deeper to the source, from the deeper to the point B here. D2B minus D1B is 6 minus 5, give me 1 centimeter. You express it in fractions of lambda. 10 millimeter divided by 1 wavelength value, 20 millimeter, you're getting it in fraction of lambda. You know this is half lambda. Half lambda coincidentally is this one. So you're going to get destructive interference. So in between, you can actually just write this one. Inside, in between the first statement and the second, you can just write, therefore destructive interference occurs. There is no displacement, no amplitude, no oscillation there because they're meeting destructively. So you want to see why it's like that, you can imagine that at point B is like this. Okay, maybe I don't need to refer to this. I can just refer to whatever you have here. You can imagine at point B, one of the waves will arrive first, looking like this. Which one arrives first here right now? At B, D1 would actually arrive first. Okay. So say right now, the wave at this one represents wave at D1, wave D1. Wave D2 will arrive later. Okay. So this one 3.2 millimeter. Okay, now wave D2 will arrive half a wavelength later. That would mean it is somewhere like this. Half a wavelength is somewhere like this. Okay, because this is one wavelength, half a wavelength is basically from here to here. All right, your wave D2 will arrive half a wavelength later. That would mean you only start to have this like this here. Okay, so now you see crest meets with trough. This is destructive. Now, because this one also has the same amplitude, your resultant wave is just going to be 0. Okay, so that's the gist of this. This is how you look at path difference. Okay, so if no problems here, then I move on to the next question. Wait, let me just see some particular questions that you can do. Okay, so I go on to that. Page 16 is okay. Page 18. All right, okay, I think we do one last example also on two-source interference pattern, but this one is also something else. Okay, we do one last question before we take a short break later on. Can you guys just have a look at page 17? All right. Okay, now this one is also talking about two-source interference, but it's using a different wave. The one in the previous page, page 16, this one is using water waves. The one that you have in page 17 is two-source interference pattern again, but it's using sound waves. All right. This one also has something to do with CRO later. You have a signal generator that is connected to two loudspeakers, L1 and L2, as shown in figure 2.1. Our microphone M connected to the Y place of your CRO detects the intensity of sound along the line ABC. The distances L1A and L2A are equal. The time base of the CRO is switched off. Okay, so the traces on the CRO when M is at A, then at B, and at C are shown in figures 2.2, 2.3, and 2.4, respectively. Okay, so this one is actually similar to the example under page, which page is it? It's actually similar to the example in page 14. Okay, page 14, I gave you some example, two source interference with sound. Is actually referring to something like this. Okay, so this is what you're having right now. What you can see here is this. Let me just clear off everything. What you do understand here is that L1 would emit its own sound wave. L2 would also emit its own sound wave. There will be regions in which waves from L1 and L2 meet. They will interfere with each other. They will overlap and then form interference patterns. Okay, the interference pattern again would look something like this, similar to what you see in the water waves. It looks something like this. Okay, so you expect to see regions of constructive interference alternating with regions of destructive interference. Okay, so doesn't matter whether it's water waves, sound waves, light waves, whatever waves, the pattern is almost always the same, alternating constructive, destructive, all right? But the way you detect them is different, all right? That's why you notice that in the notes, there are a few different experiments and a few different ways of looking at the interference pattern. So because the waves are different, the way you detect them is different. So for sound waves, you cannot you cannot see sound waves. It's not as simple as shining light onto the wave and then expecting to see a shadow of the sound wave. That one is not possible. And you cannot also put a screen along the path of the interference pattern and expect to see something like a bright and dark fringe. Sound wave does not work like that. It doesn't produce an image like light. So you cannot place a screen too. So the only way you can detect those sound waves, the interference and destructive regions of sound wave, is if you have a microphone connected to a CRO and then you move along this line. When you move along this line, you will expect to see regions of constructive and destructive. When it is constructive, you expect to hear something like a loud sound. Whereas destructive, you expect to see something, you expect to hear no sound or very soft sound. Okay? But in your case here, your microphone is connected to a CRO. It will actually display out the intensity of the sound rather than producing some sort of sound out for you. It will instead detect the intensity of the sound and display on the screen. Okay, so right now your CRO, remember I told you CRO has two settings. You have your time base and you have your Y gain. Now, time base allows the trace to move horizontally. Y gain allows your trace to move vertically. Okay. So coincidentally, in your question right now, they told you time base of CRO is switched off. That means your trace cannot move horizontally. That will explain why you don't see any horizontal trace here, because it can't move horizontally. only the Y gain was enabled. That's why you see it can only move vertically. All right. So that part is okay. Now, another important thing I should tell you here is this. They tell you distances L1A and L2A are equal. That means A is the center line because path difference is 0. Okay, whenever you see mention of distances L1A, L2A are equal, whatever, something similar, that already implies to you that that point is actually the center line. Okay, because I think I can show it from here. Okay, now I refer back to this one. This one is under page 10 of your notes, the part where I first described to you path difference. Remember, this one is your center line. Okay, so if you have wave from S1, S2 moving to the center line, this one move dot 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 here, this one move dot 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 here. Notice that the distance is exactly the same. If it is really at the center line, in between the two sources, the path difference is 0 because they travel exactly the same distance. Okay, so if the path difference is 0, the distance traveled to that point is exactly the same. That is already the center line itself. Okay, and I think one of the things I forgot to mention that time was that when your path difference is 0, it is always going to be constructive interference. Okay, because your both of your waves arrive exactly at the same time. So this one here, I could say that wave S1 would arrive like this. Wave S2 would arrive exactly the same moment. Okay, so it will give you a higher wave with larger amplitude. Okay, this one is if path difference is 0. They arrive exactly at the same moment. Crest meets crest, trough still meets trough, you getting constructed. Okay. The one that I showed you here is already having a path difference of lambda and then expand from there. If path difference is equals to 0, it looks like what I just drew here on the screen for you. Okay. Right. So yeah, back to what I was talking about. Looking at this question. All right. So you know that L1A and L2A are equal. That means that is the center line. Now for these traces, 1 centimeter represents 5 millimeter, 5 millivolts on the vertical scale. Explain why coherent waves are produced by the loudspeaker. Why do you want coherent waves to be produced by the loudspeaker? Actually, I think the answer for this was quite straightforward. They just want you to ensure that they just want you to have constant phase difference. But let's see the answer. This one is under question 2. Sorry, I overshot. Okay. Oh, sorry. They're asking you something else for this. Why coherent waves are produced by the loudspeakers? They're asking you to explain why is it that the loudspeakers are now producing coherent waves. It's because they're connected to the same signal generators. It's not asking you why the waves produced must be coherent. If they're asking you why the waves produced must be coherent, then it's to produce steady interference pattern. But they're not asking you that right now. They're asking you why is it that the waves produced by the loudspeaker are coherent now. It's because they are connected to the same signal generator. Okay. So the question asks you to find out what, using principle of superposition, explain the trace that you see at the points A, B, and C here. Okay. So the CRO screen, just now, as I mentioned to you, they said that the time-based setting is switched off. That means your trace is unable to move horizontally. If your trace was able to move horizontally, your trace would look something similar to this. This one is if time base was enabled. Okay, if time base was enabled, this would be the shape of the wave that you see on your CRO screen. But because they already disable your time base setting, your trace cannot move horizontally. Instead, it can only move vertically. That's why you see only a straight line here. Okay, so by looking at the traces that you see at points A, B, and C, you can actually say that this one is most likely going to be a region of constructive for point A. The same can also be said for point C, right? Because you see, it seems to have maximum amplitude. But at point D itself, so at point B itself, this one would most likely be destructive because you're not getting anything, all right? So you could identify the points as being constructive and destructive like this, all right? But you need to use principle of superposition to explain the traces here shown at A, B, and C. So as I mentioned to you earlier, point A, because the path difference, they say L1A, at point A, the path difference is 0 because the distances L1A and L2A are equal. So this one, I already know it must be the center line, all right? So at the center line, that's where point A is. I know it's constructive interference. At the same time, I know that its path difference over here is equals to 0 because it's the center line, all right? So I will say something along these lines where I say waves that overlap at point A have path difference of 0, therefore there is constructive interference. Okay, that's all they just needed you to say. They want you to explain little what is the nature of the path difference and then whether it's going to be constructive or destructive. So you really only just need to say this. The waves at point A have 0 path difference, hence it will have constructive interference. All right, that part is okay. Okay, then what about at point B? Point B is this one here. Point B is this one here, where you had 0 reading. So that one is most likely going to be a destructive, okay? But how sure are you that this is actually the first dark fringe? It could be the second, it could be the third, it could be the fourth. You just don't know. The question merely mentioned that it's point A, B, and C. They didn't mention that all these are adjacent to each other. It could be that maybe they go and take point A randomly here, and then they jump a large distance to point B, and then they jump a large distance to point C. They didn't tell you points A, B, and C are adjacent to each other, meaning to say one, just write one after another. They didn't say that, right? So although you can identify point B as a region of destructive interference, it's actually not the, probably you cannot say it's the first point where you have destructive interference. Sorry, I used the wrong term here. This is not dark fringe because it's not light. Okay, so probably it's better if I just write this as the first minima. Okay, all right. Here B is destructive, but I am not sure whether it's going to be the first minima. It could be the second, it could be the third, it could be the fourth. The question never said that the points A, B, and C are right adjacent to each other. Okay, they didn't say that, so I cannot assume that this one is actually the first minima. It could be the second, it could be the third, it could be the fourth. All right, so because you're not sure, you cannot be specific about the path difference. You use a general path difference, which is n plus half lambda. Okay. All right. So that's why here your answer says this. The waves that overlap at B have a path difference of n plus half lambda. So there is destructive interference. They didn't give a specific path difference because we do not know whether it's the first minima, second minima, third minima, or fourth minima. All right, so we give it a general path difference, n plus half lambda. All right. So that one is for this. Okay, then for point C, it's a bit similar again. I know that point C is going to be a point of constructive interference because I seem to have a very large amplitude here. So again, you do not know whether that region of constructive interference is going to be your first maxima or second or third or fourth. You just don't know. All right, so you just again give it a general path difference, right? Where you say that because it's constructive, the path difference definitely must be n lambda. Okay, so you will write something like what is written here. Okay, let me write off the things. For point C, the waves overlap have path difference of n lambda, thus there is constructive interference. That's all there is to it. Okay, so that one should be okay. Right, so if nothing else, let me just clear off everything and do the last question before I move on to diffraction grating. Okay, now look at part B. Part B, they tell you, yeah, you have that question. They tell you the sound emitted from L1 and L2 has a frequency of 500 Hertz. The time-based setting on the CRO is now switched on. Okay, so if before they switch it off, now they switch it on. The microphone M is placed at A, at the center line. On figure 2.4, draw the trace seen on the CRO. On the vertical scale, 1 centimeter represents 5 millivolts. On the horizontal scale, 1 centimeter represents 0.1 milliseconds. Okay. So right now, you want to draw the pattern that you see. You want to draw the trace that you see at point A, which is this one. So as I mentioned to you, this one came about because you remove your time-based setting. You disable your time-based setting. If you had enabled your time-based setting, you should have been seeing something like this. Okay, so you are trying to draw this right now with time-based setting enabled. Okay, so on this figure, draw the tracing. All right, the tail 1 centimeter is 5, 1 centimeter is 0.1 for the line gain and the time base respectively. Okay, so if you look at this one, right, if you just look at the previous page, the one that shows you the CRO screen, one common thing that people somehow mistook was they say that this one was A. This entire length is A. This is not correct. Your A is really only supposed to be half of the length that you see here. Okay, so this is actually supposed to be your amplitude. This is the correct amplitude. All right, so right now you want to draw the wave that you see there. Okay, so let me just base it on what you have here. Okay, they also told you that your sounds have frequencies of 500 hertz. Okay, L1, L2 at 500 hertz. All right, when they overlap to give you your resultant wave, when waves from L1 and L2 overlap to give you your resultant wave, which is shown here. The frequency and period does not change, all right? So although they tell you L1 and L2 is 500 Hertz, after the superposition, the frequency and period does not change. Okay, the only thing that will change is only the displacement. Okay, so they gave you the frequencies of both sound waves already as 500 Hertz. After the two waves overlap and give you a constructive interference, the period doesn't change, the frequency doesn't change, it remains the same as before. So what you want to do now is that since frequency is 500 Hertz, what is the period? The period is 1 over frequency, 1 over 500, giving you 2 times 10 power minus 3 seconds. Change to milliseconds is 2 milliseconds. All right. So from what I can see here, my period is going to be 2 milliseconds. All right. My amplitude is just going to be 5 millivolts. Did they say anything here? The CRO, okay. Yeah, okay. So they say now this is the same CRO screen, but with the time-based setting enabled. All right. So they want you to draw the new trace that you see here. Okay. So, but notice that I'm not showing the entire waveform. I'm actually just showing you the half of waveform, which was only from here to here. Okay. Right. So let me just go back to this one. If you look at this one is period of 2 milliseconds, all right? And then this one, I know that this one is worth 2 centimeter, but this is not the amplitude. The amplitude is only worth 1 centimeter on the CRO screen. Okay, so with that in mind, you look at your CRO screen here. This one is 1 centimeter. So your wave amplitude will really only be 1 centimeter. Okay. You should only occupy 1 centimeter here. All right. Now, why is it that it doesn't show you the full waveform? It's because you see, they told you 1 centimeter represents 0.1 milliseconds. 1 centimeter or 0.1 milliseconds. Now you look at how many centimeter is this. This one would be 10, I think. 1, 2, 3, 4. I mean, if you calculate it properly, it will be worth 10 centimeter. So if you're talking about 10 centimeter, 10 centimeter would be representative of 0.1. So it will be representative of just 1 milliseconds. Okay. So the reason why you cannot show the full waveform here is because this time-based setting is only up to 10 centimeter. It can only cover up to 1 millisecond. But when you look at your waveform, one complete period is 2 milliseconds. So you cannot fit everything in. You will only be able to fit in half of your wave. That's why here, you're drawing only half of the wave. and it seems to be stretched out a lot because this one is representative of 1 millisecond. Okay. All right. Okay, so this one should be okay. Oh yeah, another thing I probably may have missed out is this one. Your question here on the previous page, they already mentioned 1 centimeter represents 5 millivolt on the vertical scale. Okay, so over here just now, I know that this one is 1 centimeter is actually 5 millivolts. Okay, so this one from here, I know that this one is t equals to 2 milliseconds. I also know that the amplitude is actually 5 millivolts. Okay, because here I see it is 1 centimeter, but here they also say 1 centimeter is 5 millivolts, so I know this is 5 millivolts. So when I want to translate it to the CRO screen here, they also already say that 1 centimeter is 5 millivolts. So 5 millivolts from the previous CRO screen translated to this trace will also still be 1 centimeter. There's actually no change. Okay, right. So that's the one thing to notice here. Other than that, everything should be fine. Okay, so I think we just stop here for the double slit. There are actually a lot more a lot more examples to do, but this one we can do later on slowly. Okay, so this question is all right. Then I will just move on to the next part of your lesson, which is on diffraction grating. Okay, so I'll refer back to the notes now. Okay, if you are okay with double slit interference of light, diffraction grating will be very, very similar to it. All right. So can you just refer to your notes, page 16? Sorry, not page 16, page 15. All right. Have a look at page 15. Okay. Now, diffraction grating, this one is mostly used for light only. All right. Diffraction grating is not two source interference. Okay. Actually, is multiple source interference. The interference that you've learned so far before is all from two sources only. But when it comes to diffraction grating, you're also talking about the interference formed by them, but this time the source is just not, it's not limited to only two sources. It actually comes from many, many, many different sources. All right. So what we'll say here is this. If you remember that under double slit, I'm just going to draw it here. Under the double slit experiment, you had a slit, you had two slits, a double slit. You shine light through the double slit, and then on a screen that you place far off behind, you're going to get a pattern of bright and dark fringes, or pattern of maxima and minima. Okay, so this is what you see. And then the equation you use was lambda equals to ax divided by d, where we tell you that this one is a, and then this one is d, and then this one is actually x. Okay, now when it comes to double slit interference pattern, you're also going to be doing something similar to double slit, where you shine light through something, but instead of using a double slit like what you're doing here, you replace it with diffraction grating. So a diffraction grating is actually similar to a double slit, just that it has many more slits than just two. So double slit would just be something that looks like this with two slits, but diffraction grating has many slits. All right. So right now for diffraction grating, you will shine light through a diffraction grating. You will also place a screen behind the diffraction grating, and then you will actually also start to see interference pattern on the screen. All right. When light is shown through the grating, you will actually see an interference pattern of bright dots that is symmetrical about the central beam. So if this one is showing you your diffraction grating, you shine light through the diffraction grating, the beams of light will separate. These beams of light actually represents your regions of constructive interference. All right. So if you place a screen behind, you eventually end up seeing bright dots of light that is symmetrical about your central beam. This is your central beam. So they are actually symmetrical about the central beam. Okay. So the way in which you're going to form, so needless to say, these bright dots that you have here are actually due to constructive interference, much like the case for double slits. All right. But the way they are formed is slightly different. I mean, it's similar, but with some slight variation. What we'll tell you is this. If I were to give you a diffraction grating, okay, let me just give you an example. If you recall from the double slit experiment, this one was your center line. This one is my first bright fringe. Okay, so if this one is my double slit with slit 1 and slit 2 here, under the concept of path difference that I explained to you, wave from S1 and S2 will arrive at this point, and they will interfere constructively to give you that bright spot, the bright fringe. And then they have a certain path difference to them. The difference in the path that they travel will determine whether it's constructive or destructive. In the case of the first bright fringe, what was mentioned to you was that the path difference is actually just lambda. Wave S1 will arrive one wavelength later than wave S2. They interfere constructively, giving you your bright fringe. Okay. Now for diffraction grating, it is a similar concept. Okay, it's a similar concept where you have your bright spots. You're also supposed to have constructive interference there. And then when it comes to the path difference, it's the same. All right. So what do I mean by that is, let's just say that this is my diffraction grating. All right, with many slits. And then say this one is my screen that I place behind. Okay. Say for example, this one is my center line. This is my center line. I know that I have a bright spot here, constantly interference, but some distance away, I also have another bright spot. Say this is my first bright dot or maxima. Okay. Now, right now for diffraction grating, as I mentioned to you, you do not have only two slits. You have many slits. So you could have S1, S2, S3, S4, S5, and so on and so forth. So when the waves from your diffraction grating arrive at this particular spot, all the waves from each of these slits must arrive at this spot in order to give you your bright dots. So what we'll say here is that S1 will arrive here, S2 will arrive here, S3 will arrive here, S4 will arrive here, and then S5 will arrive here. So you can see that they all don't arrive at the same time. there's actually a difference in the distance that they travel to that spot, okay, to this spot. There is a path difference. So in my case here, for me to have a bright dot here, my first bright dot or my first maxima, my path difference is actually also still lambda, but the path difference must be lambda between each subsequent wave. What it means by that is that between wave S1 and S2, between wave S1 and S2, when it arrives here to give me the bright spot, to give me the constructive interference, this path difference must be equals to lambda. And then for wave S2 and S3 to arrive at that same spot, the path difference again is lambda. And then for waves S3 and S4, when it arrives here, the path difference must be equals to lambda. You see, from one pair to another, the path difference is always just lambda. Okay, that's why here the diagram mentioned here, in the direction of the first order maximum, the waves are in phase, but each one has traveled a wavelength further than the one below it. You can imagine that if this one is your bright spot, each of these waves from each of these slits will arrive at this spot, but the difference between each of these waves in terms of the path difference is just lambda. Okay, that's why here in the notes I also mentioned this. For any maximum, the path difference between each subsequent wave must be equal to whole number of wavelengths, right? So if this one is the first bright dot, each subsequent wave must have a path difference of lambda, all right? If you're talking about the second bright spot, like this, the second bright spot, or second bright dot, or maxima, whatever you want to call it, the path difference must be equal to 2 lambda between each subsequent wave. All right, each pair of waves that arrive must have path difference of 2 lambda, each subsequent pair. All right, so that is what we mean. That's why I mentioned it's somewhat similar, but you have to look at it slightly differently. Okay, you see, between S1, S2, path difference is lambda. S2, S3, path difference is also lambda. S3, S4, the path difference is also lambda. But you compare S1 and S4, the path difference is actually going to be 3 lambda. So that one will be different. Okay, but we don't look at it that way. We look at each subsequent pair of the waves. All right, that one, the path difference is lambda. Okay. Right, but don't worry so much about this. When it comes to the exam questions, we don't really care about the path difference for diffraction grating. We don't really test you on the path difference for diffraction grating. We really only test you a lot on the path difference for double slit. Most of the questions that relate to path difference, that one is usually only for two source interference patterns. It's usually mainly used for your double slit. It's not used for diffraction grating. Okay, but when it comes to the formation of the bright spots on the diffraction grating, it does use the concept of path difference. Just that we say that each subsequent pair must be n lambda. All right. Okay. So when you have light that passes through a diffraction grating, okay, when you have light that passes through a diffraction grating, the lights will spread out. It will form certain regions of constructive interference, certain regions of destructive interference. You can see those regions or those interference pattern on the screen if you place a screen behind the diffraction grating. Okay, it will be summarized in the diagram that you're seeing in your notes right now under page page 16. Okay, so basically what you do is you erase off a lot of this unnecessary stuff. Okay, so what you do is that you shine a light onto your diffraction grating like this. The beam of light will spread. This red lines here represents your region of constructive interference. Okay, so after that, you place a screen right behind the diffraction grating. What you then see is a pattern of bright dots, similar to your pattern of bright and dark fringes for double slit. Okay, but when it comes to the calculations for the patterns formed by diffraction grating, you do not use you do not use lambda equals to ax over d. This one is strictly speaking only for two source interference, such as your double slit. Okay, this is specific only for double slit or two source interference pattern. For interference pattern formed by diffraction grating, you have to use a separate equation. That one is actually d sine theta equals to n lambda. Okay, this one is specific only for diffraction gradient. And every time you see mention of diffraction gradient, you need to use this. Okay, I actually wrote it at the top part here. Okay, where we tell you d, small d here is the slit separation, n here is the order number, then theta is the angle of diffraction. So d, this is where the confusion starts to arise for some people. In your double slit, we also have d, but it's capital D. Capital D here refers to the distance between the slit and the screen. Okay, but here under diffraction grating, we also have d, but it's small d. Small d here refers to the distance between the slits. It's actually this part here. Where is it? It's actually this part here. Okay, distance between the slits. So don't mistake this d and the other d. Okay, the small d here for diffraction grating is for distance between the slits. All right, and then after that, we have n. N is the order number. Okay, usually for diffraction grating, when you form the interference pattern on the screen, they are usually labeled according to order. The center bright dot is normally called the zero order. It's labeled n equals to 0. And then after that, as you go further from that center, from the center line, you start to number it 1, 2, 3, 4, 5. So if I go upwards here, this is the first order, second order, third order, fourth order, so on. And then after that, on the other side below, it will still be labeled 1, first order, second order, third order, fourth order. All right. So that is what the n there means. All right. And then the other thing here is the angle theta. Okay. Angle theta here refers to the diffraction angle. All right. We call it diffraction angle of the nth order. What do we mean by that is this. If say, for example, I'm doing a calculation that involves first order. The angle, the first order is this line here, right? Okay, this is the first order bright dot represented by this line. If I'm doing any calculation that involves the first order, the angle I use must be the angle for the first order, which means it is the distance between the center line 0 and the first order. This one is actually my theta 1. If I go and do some other calculation, but then the order number I'm considering is 2, then I must use the second order diffraction angle. So what I'll do is that this one is my center line. My second order is here. This is the angle of diffraction. Okay, this is what we mean by the angle. All right, it's actually the distance between that order that you're considering and the center. All right. Okay, then another thing that you should know here is what are the differences between your what are some of the differences between the interference pattern formed by your double slit and your diffraction grating. That one is summarized here. Okay, so normally we tell you that the bright dots refer to a maxima are more widely spaced than a double slit. Okay, you could be using red light. You shine it through a double slit, and then you get a pattern of interference fringes, bright and dark fringes. You notice that there's a certain spacing between the bright fringes, correct? If you shine that same light, say red light, to a diffraction grating, you're still going to get a pattern of interference fringes represented by dots, bright dots on the screen. But generally speaking, we'll tell you the distance between the dots is actually much wider than that of a double slit. That's what this statement means. They are more widely spaced than with a double slit. Okay. So just now I mentioned that the central fringe is called the zero order. The next dot is the first order maximum and so on. And then another key difference here between double slit and diffraction grating is this. The maximas are not equally spaced, and the angles between the adjacent maxima increases with order number. So remember last time in the summary for double slit, I mentioned that in the summary for double slit under page 12, I mentioned that the x is the same. If let's just say under page 12, there was a summary of the double slits, right? Okay, I told you the fringes are equally spaced. The distance between adjacent fringes remain the same regardless of distance from the center line. So what was I saying then was that if you go further away from your center line, the distance between the fringes actually do not change. Okay. So if I look at the diagram on the right hand side right now, if I go further away from the center line, this x and this x will always remain the same. I can also go on to the next pair of fringes. The x will also remain the same. They won't change. Okay. But when you're talking about a diffraction grating, okay, if you talk about diffraction grating, let me just erase everything here. This distance x1 and this distance x2 and maybe another distance x3, what will happen is that they're not going to be the same. X3 is not the same as x2, is not the same as x1. Instead, x3 is going to be more than x2, is going to be more than x1. That's what this statement here means. They are not equally spaced. Okay, and the angles between the adjacent maxima will increase with order of magnitude. So it could be that between here and here, your angle is 10 degrees. But then after that, for this one and this one, the first order and second order, your angle is not the same. Maybe it becomes 20 degrees. And then after that, you go on to the next one, between the third order and second order, your angle becomes, say, maybe 40 degrees. All right. So it's because the angle keeps increasing. That's why the distance between the fringes or distance between the bright dots keep increasing. They won't be equally spaced. Okay. So that is one thing different between double slit and diffraction grating. Double slit spacing will always be the same. Diffraction grating spacing will not be the same. Okay. It will tend to increase with distance from the center line. because the angle keeps increasing. All right. And also for diffraction grating, the maxima tends to be a lot sharper and brighter than double slits. For double slits, you tend to see the bright fringes as being a bit fuzzy, but for diffraction grating, you tend to see the bright dots as quite sharp. All right. Okay, so that is one of the main differences for diffraction grating. Okay, then I go through some little parts here again for you. All right, just now I mentioned to you slit separation is represented by the symbol small d. A lot of times when you're doing calculations for diffraction grating, they may not give you the slit separation directly. Instead, they tell you something else. They will tell you that the diffraction grating has don't know how many number of slits per unit length. Maybe they tell you, okay, the diffraction grating has 100 lines per millimeter or 1,200 lines per millimeter. That one is this quantity here. Okay, it tells you how many lines are there in a certain distance. You want to find slit separation is this. So the relation between the number of slits per unit length and slit separation D is given by this equation. D is 1 over n. All right. Is something similar to this. Why is it D equals to 1 over n? If I tell you you have 100 lines per millimeter, okay, that means 1 millimeter has 100 lines. So D would be akin to you taking 1 millimeter divided by 100 lines. So this one will give you 1 times 10 power minus 2 millimeter. Okay, that's the understanding here. I could also give it to you in some other values. Let's just say 1,200 lines per centimeter. That means 1 centimeter has 1,200 lines. So I want to find the slit separation. I take 1 centimeter divided by 1,200. Okay. I'm basically taking 1 centimeter divided by 1,200 lines. So I'm going to get 8.33 times 10 power minus 4 centimeter. Okay. So these are the slit separation. So I may mention here, if n is given in number of lines per millimeter, then d will be in millimeter. Similarly, if n is number of lines per centimeter, then d will be in centimeter, because the understanding is that you're taking whatever unit of the per unit length divided by the number of lines, your unit will be following the original unit. Okay, if it's something per millimeter, the d will be in millimeter. If it's something per centimeter, then your d will be in centimeter. Okay, so be mindful of this. All right. Okay, then the next thing I just want to talk about is when you do your questions on diffraction grating, you will also be asked to calculate one of two things. Calculate the maximum possible order number, or calculate the total number of bright dots and maxima. So just now I mentioned to you, when you shine light onto your diffraction grating, your light will tend to spread out. And then after that, you place a screen behind and you see a pattern of bright dots. So I mentioned specifically to you, the bright dot or maxima at the center is 0 order, and then from there you start to label it first order, second order, third order, and is symmetrical about the center line. So the order number cannot increase indefinitely. It will reach a maximum eventually. So you cannot go up to the 99 order number. Depending on the wavelength that you use, depending on the slit separation that you use, you will eventually reach a maximum order number. You can only produce a certain order number, maximum order number. So some questions will ask you to calculate what is the maximum order number. All right. So what you do is that you use your diffraction grating equation where we tell you d sine theta is n lambda. N is in turn going to be, what we'll tell you is that n lambda is over d is equals to sine theta. Now you know that sine theta can never be greater than 1. The maximum value of sine theta is just 1. It will never be greater than 1. So this equation becomes like this. Okay? Because sine theta cannot be more than 1, the equation becomes this: n lambda over d less than or equal to 1. So n max is actually going to be d divided by lambda. All right, your maximum order number can be found from this equation: the ratio of your slit separation divided by your wavelength. Okay, sometimes in your marking scheme they don't use the inequality equation, they just say n max is actually d over lambda. You will eventually see this being used in your marking scheme. Okay, so to find your maximum order number, you need to use the ratio of d over lambda. Whatever value you get, this is very important. Whatever value you get, you must always round it down to the nearest integer. What do I mean by that is that it could be that your n is maybe 4.1. This one rounded out will just be 4. But what if your n is 4.8? In normal maths, you would have probably round this to 5. This one, no, don't ever do this. You round it down to nearest integer, meaning to say it's supposed to be 4. Okay, so this one, just be careful of this. When it comes to finding maximum order number, you will always need to round it down to the nearest integer. Don't round it up like you do normal maths. Okay, so that part is okay. All right, then the last one that I just need to mention before I end the class for you is that sometimes rather than finding maximum order number, they will ask you to find the total number of bright dots or maxima. So remember, one of the first things that I mentioned to you just now was that the interference pattern that is formed is usually symmetrical about the center line or the central maximum. So meaning to say, normally you have 2 first order maxima, 2 second order maxima, and so on. You can actually see over here. Okay, you have 1, 2, 3. You also have 1, 2, 3. Okay, so you see this one here, third order is your n max. Okay, let's just say this is your n max right now. If we are asked to find the total number of bright dots or maxima, it means they want you to find what is the total number here. So an easy way to do that would be to take the highest order number, multiply with 2, plus with 1. Okay, because you see here, first, second, third, this one is already 3. If you somehow multiply with 2, you're going to take into account this one too. All right, but there's another one that you haven't taken into account, which is the center one. So that's where your plus 1 came about, is because you're adding the 0 order inside. So this one will give you the maximum order. This one will give you the total maxima, total number of maxima. Okay, so there's a difference between calculating maximum order number and calculating the total number of maxima. This one you need to read carefully the question, what they want.